Hi everyone, today a video on amount of substance and specifically to do with the ideal gas equation. So the volume of a given mass of any gas is not fixed. The volume can change if we change the pressure and if we change the temperature. But there are several simple relationships that connect pressure, temperature and the volume of the gas, and these were all worked out many years ago. The first is something called Boyle's law. And he worked out that the pressure times the volume was equal to a constant for a fixed temperature. Charles' law states that the volume divided by the temperature is equal to a constant at a fixed pressure. And the Gay-Lussac law says that pressure divided by the temperature is equal to a constant for a fixed volume. Now, if we combine all of those three laws together, this gives us that the pressure times the volume divided by the temperature would be equal to a constant for a fixed mass of gas. So combining Boyle's law, Charles's law and Avogadro's law, or Gay-Lussac's law, comes in to the ideal gas law and the ideal gas equation. And so the ideal gas equation says that the pressure times the volume is equal to the number of moles times the gas constant times by temperature. Now there are several assumptions we make. We talk about this thing of course an ideal gas, and what we mean by that is that there are no interactions between the gas molecules. The gas molecules don't interact with each other. They're not attracted to each other, they're not repelled by each other, they don't interact at all. We say that the gas particles only possess kinetic energy. They don't have any potential energy, it's only kinetic energy. And they only collide with each other in elastic collisions. This means there's no loss of kinetic energy. The kinetic energy before and the kinetic energy afterwards is conserved. We also say that the volume of the molecules is much smaller than the volume occupied by the gas. So if I have a container of a certain volume, the actual size, the volume of the molecules is very tiny compared to that total volume. And the molecules are in random chaotic motion, something we call Brownian motion, essentially flying off all around the place in random motion. And they obey Newton's laws of sort of classical mechanics. And the final one is that the gas molecules are these kind of perfect hard spheres. So going back to the equation, PV equals nRT, it's important to know the units for all of these quantities. So pressure is measured in a unit called pascals. Now pascals is the same as 1 Newton per metre square. Quite often pressures are given in kilopascals. So it's important to be able to convert from kilopascals to pascals, timesing by 1000. Volume has to be in metres cubed. The number of moles has the unit of moles. The molar gas constant is equal to 8.31 to 2 decimal places, and this has the units of joules per Kelvin per mole, and the temperature is in Kelvin. Now the number of moles will always be given to you in moles, and the molar gas constant is just a constant and will be given to you, but it's really important to make sure that no matter what the values that you're given in the question, the units for them, that when you put the numbers into the equation, that pressure is in pascals, the volume is in metres cubed, and the temperature is in Kelvin. So this brings us on to talk about unit conversions. We've already looked a little bit at unit conversions and converting between decimeters cubed and centimeters cubed. The way that I remember this is that 1 metre is the same as 10 decimeters or 100 centimeters. And so we can say that 1 decimeter is the same as 10 centimeters. So 1 decimeters cubed is 1,000 centimeters cubed. So to convert between a decimeter and a decimeter cubed and a centimeter cubed, we times by 1,000. And a decimeter cubed is the same as 1 meter. So remembering that our SI units for the ideal gas equation, the units we have to use in this equation, are meters cubed for volume, Kelvin for temperature, and pascals for pressure. If we're given a pressure in kilopascals, then we have to times that by 1,000 in order to get to pascals. Remember that the kilo prefix there means timesing by 1,000. Quite often the temperature will be given to you in degrees Celsius rather than Kelvin, and the conversion here is that we have to add 273. So 25 degrees Celsius is the same as 298 Kelvin. Sometimes the volume will be given to you in centimetres cubed, sometimes it will be given in decimeters cubed. And so if we want to convert from decimeters cubed into meters cubed, we need to divide by 1,000 or 10 to the 3. To convert from centimetres cubed to meters cubed, we have to divide by 10 to the 6 or a million. And one of the ways that I remember this is to think, okay, how do we convert from centimetres to meters? We divide by 100. And so to cube all of this, centimetres cubed to meters cubed is dividing by 100 cubed, or 10 to the 6, a million. From decimeters to meters, I divide by 10. So decimeters cubed to meters cubed is dividing by 10 cubed, 1,000. So time to have a go at some questions. So we have questions here relating to the ideal gas equation. If you want to have a go at these questions, pause the video and the answers will be on the next slide. So the first question asked us to calculate the volume occupied by 1 mole of a gas at 25 degrees Celsius and 100 kilopascals. So we have our ideal gas equation. PV is equal to nRT. In this case, we need to rearrange this equation to find the volume. So in order to do that, we're going to divide both sides of the equation by the pressure, such that our volume is equal to nRT divided by P. Then we have to put our numbers into the equation. The 1 mole is in the units of moles already, so that's fine. However, our pressure was given to us as 100 kilopascals, so our pressure needs to be converted into pascals, so it's 100 times 1,000 or 100 times 10 to the 3. And then our temperature was given to us as 25 degrees Celsius. Remember, the conversion from degrees Celsius to Kelvin is adding 273. So we put these numbers then into our equation, and the ideal gas constant is 8.31. And the volume comes out to be 0.0248, and we remember that our volume is measured in meters cubed. Make sure we always have a unit for these numbers. So this is roughly the same as 25 decimeters cubed. And one of the interesting things with the ideal gas calculation is that this would be true for any ideal gas at room temperature and pressure. So it doesn't matter whether we're considering nitrogen to be the ideal gas, or helium to be the ideal gas, or oxygen to be the ideal gas. Because this equation doesn't actually consider the actual gas we're dealing with, it just considers the number of moles, the temperature and the pressure, we can say that for any ideal gas, the volume occupied at room temperature and pressure is roughly 25 decimeters cubed. Of course, this is one of the breakdowns of the ideal gas calculation, that obviously the true volume occupied by oxygen versus nitrogen versus helium is different, and that comes down to those assumptions we talked about, the idea really, the key one being that the molecules don't interact with each other. Of course, in reality, they do. The second question is to calculate the temperature of a gas if 0.5 moles occupy 0.6 decimeters cubed at a pressure of 300 kilopascals. So again, we're going to rearrange our equation now for temperature. So we divide both sides by nR. This gives us that T is equal to PV divided by nR. And then again, we just have to be careful with our units here. So the moles are given to us in the unit of moles, that's fine. Our volume, though, is given to us in decimeters cubed. Remember that the conversion to get from decimeters cubed to meters cubed was to divide by 1,000. That's the same as timesing by 10 to the minus 3. So we put 0.6 times 10 to the minus 3. We have our ideal gas constant, our molar gas constant, 8.31. And then we have our pressure of 300 kilopascals. So we have to convert, again, the 300 kilopascals into pascals, which is timesing by 1,000, or 10 to the 3. And when we put all these numbers in, we get a temperature of 43. And remember that the temperature is in Kelvin, so 43 Kelvin. Also notice again the use of significant figures. So we have to give our answer to the minimum number of significant figures. The 300 kilopascals is 3 significant figures. The 0.500 moles is 3 significant figures. The gas constant is 8.31, that's 3 significant figures. But our volume was given to us as 0.60. That's 2 significant figures, so we have to give our answer to 2 significant figures. The third question was to calculate the mass of the CO2 sample of gas. So now we're going to work this out. If we're going to be working out a mass, first of all we need to work out a moles, because obviously mass isn't directly included in the equation. We have PV equals to nRT, but from out of those 5 variables, which one of those can we get to mass from? Well, we can get to it from moles. So we have to rearrange for moles. We divide both sides of the equation by RT, so we get that moles is equal to PV divided by RT. And again, just make sure that we have our numbers being put in the right units. So we have 17 degrees Celsius. We have to add 273 to turn it into Kelvin, so that's 290. Our gas constant is 8.31. We have our volume as 40 decimeters cubed, so again we have to divide by 1,000 to convert that into meters cubed, or times by 10 to the 3, it's the same thing. And then we had 150 kilopascals, which we have to times by 1,000, or 10 to the 3. By putting all those numbers in, we end up with a mole value of 2.49. Again, note the use of the significant figures. The minimum we've given is 3, so the answer has to be to 3. But of course, this isn't the end of the question. That's worked out the moles, not the mass, so we have to use our equation, which is that the moles is equal to the mass divided by the mR. We're not talking about a solution here, so we use the m over mR equation. Rearrange for the mass, so times both sides by the mR, and we get that mass is equal to moles times mR. Put the numbers in, and we end up with 109.5 grams. But note that we have to give our answer to 3 significant figures because the minimum significant figures in the question was 3. So this is 110 grams. Finally, question 4. So the first part of this was to calculate the volume of hydrogen gas evolved when we've added sodium to water. So the first thing in questions like this I would always do is write the chemical equation down. So we're going to put sodium into water, sodium plus H2O. This is going to produce sodium hydroxide and hydrogen gas. We then have to balance up our equation, and in doing this we have 2 sodiums, 2 lots of water and 2 lots of sodium hydroxide. So we have enough data in the question to be able to calculate the moles of sodium, even if you're not necessarily sure how to go about the question. We have sodium, we know the atomic mass of that, and we have the mass that we put in, so we can work out the moles using m over mR. In doing so, we find that we have 0.0226 moles of sodium. And then we need to look at the mole ratios. 2 moles of sodium react with 2 moles of water to give 2 moles of sodium hydroxide, but only 1 mole of hydrogen. So the moles of hydrogen are half the amount of moles of sodium, 0.0113 moles. So now we actually have the moles of the hydrogen. We can now put that into our ideal gas equation to work out the volume produced. So we rearrange for the volume, we divide by pressure, so we get that volume is nRT over P. And then again, we just have to make sure that our units are right. So our moles are obviously in the unit of mole, so that's fine, 0.0113. Our gas constant, 8.31, is fine. Our temperature was 25 degrees Celsius, so we have to add 273 to get 298 Kelvin. And then finally, we had a pressure of 100 kilopascals, which we have to times by 1,000 to get to pascals. And in doing so, we will find that our volume comes out to be 2.80 times 10 to the minus 4 meters cubed. Then part B was asking about the concentration of the sodium hydroxide solution formed. So if you're not happy with concentration calculations, I recommend going back to the previous video in the series and looking at those questions. But we can also use our mole ratios to say that we have 0.0226 moles of sodium hydroxide, same amount of moles as we had of sodium, or twice the amount of moles we had of the hydrogen, because it's essentially a 2:2 or a 1:1 ratio. And then because we're talking about solution moles, we need to use our solution equation, which is concentration times volume. I've written it here as concentration times volume divided by 1,000. Remember, that's just to convert the volume, which we are given in centimeters cubed, to a volume that's in decimeters cubed, so dividing by 1,000, because our concentration is always measured in moles per decimeter cubed. So we rearrange for concentration, we times up by 1,000, divide by the volume, so the concentration is N times 1,000 over V. And what this ends up giving us here is, when we put the numbers into our equation, we get 22.6 moles per decimeter cubed. So thank you for watching this video. You can find many more like this on my YouTube channel. If you found this video helpful, please leave a review on a tuition website. I offer tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you ever need any more help with your chemistry, you can always feel free to email me. I'll be happy to help.